There we go. The root of the word chlorine is chlor, so that's, oops, I don't want to write a C, hydrochloric acid. Now the rest of these are oxyacids. So the way that oxyacids work is you have to look to see what the name of the anion is, and then based upon the end of the name of the anion, that determines what the name of the acid's name has to have as a suffix. So for instance, HNO3, this NO3, that's the nitrate anion. So when you look on the ion chart, NO3 is nitrate. And because it ends with 8 always changes to ic. So the name of the acid is not nitrate acid, but 8 changes to ic. So that's nitric acid. On the other hand, HNO2, when you look on the ion chart, that's nitrite. And if the end of the name of the anion ends with ite, it changes to us. So instead of nitric acid, that's nitrous acid. Not to be confused with nitrous oxide, which is a gas that's different than nitrous acid. So nitrous can be used for a couple of different purposes, either nitrous acid or some other nitrous compound. So if you're here, if people talk about like nitrous, like you can use nitrous oxide and inject that into the intake manifold of an automobile to give you additional horsepower or boost. They just call it nitrous. That's nitrous oxide, not nitrous acid. Nitrous oxide is also known as laughing gas. It's used as a sedative uh, in like if you have dental work done and they use gas to kind of knock you out, they call it laughing gas. That's nitrous oxide, not nitrous acid. So H3PO4, when you look at PO4, that's phosphate. And again, if it's 8, it changes to ic. But that's a little bit tricky because you might have written phosphic acid, which isn't quite correct. It's because the phosphate is in phosphorus, it's phosphoric acid. The root of the word phosphorus is phosphor. So although the name of the anion is phosphate, you don't just change phosphate to phosphic. The phosphate comes from the phosphorus and it's phosphoric acid. You'll get used to hearing and seeing those. It's not as if you have to memorize those exceptions, but phosphorus and sulfur are two good exceptions to how the rule's a little bit different for some of them. All right, CO3, that's carbonate. Because it ends with 8 changes to ic, and that's called carbonic acid. Sorry, my pen is being slow, so it doesn't write too smoothly. I got to fix it. Carbonic acid. HC2H3O2. So this C2H3O2, you'll find that's called acetate. And 8 changes to ic. So that's acetic acid. And acetic acid has another common name, vinegar. That's what vinegar is. Vinegar is used in cooking. It's used as a cleaning agent. Vinegar's real name is acetic acid, and its formula is HC2H3O2. It's hydrogen with the acetate anion, and it's dissolved in water. So that's how those go. Those are the right names: hydrofluoric, nitric, nitrous, phosphoric, hydrochloric, carbonic, acetic. The ones that are binary, I wrote in red. They all have the names like hydroic, and then any of the oxyacids that end with 8, including nitrate, phosphate, carbonate, and acetate, the names end with ic, nitric, phosphoric, carbonic, and acetic. And then the ones that end with ite, I guess that was just nitrite. Nitrite changes to nitrous, so that was nitrous acid. All right, then same thing here. If it has hydro and ic, it's just binary. So hydrofluoric acid, that's with fluorine. But you got to look at the ions. So it's always hydrogen, and then whatever the anion is. Hydrofluoric is fluorine, F1 minus. So the formula is just HF. Hydroiodic acid, H1 plus, and iodine is I1 minus. So it's just HI. But then sulfuric came from sulfate. When you look at sulfate, that's SO4 3 minus. So when you write the formula, you've got hydrogen, and sulfuric came from sulfate. Sulfate is SO4 3 minus. So the formula has to be H3 SO4, because you're going to need 3 hydrogens to go with every 1 sulfate to make it neutral. Sulfurous acid came from sulfite, and the sulfite anion is SO3 2 minus. So whenever you make the compound between hydrogen and sulfite, it's got to be H2 SO3. Oh, sorry about that. I was looking at, this is not right. It's just H2SO4. I even know that. 2 minus H2SO4. SO3 is 2 minus H2SO3. Nitric came from nitrate. So this H plus, and then the nitrate anion is NO3 1 minus. So it's just HNO3. Hydrogen 1 nitrous. So nitrite or nitric came from nitrate. Nitrate is NO3. So HNO3. So those are the right answers to that. We're going to do a whole lot more practice with writing names and formulas for ionic compounds and acids, but you got to get good at that. So, all right, let's see. Okay. In the, oops, I want to do that. Desktop. Okay, in the folder for this week, it says HC, or honors chemistry, naming hydrocarbons only. I want to go through some of this. So there's a whole class of ionic compound or covalent compounds that are called hydrocarbons. And hydrocarbons, you might not be surprised, are compounds that are made of hydrogen and carbon. So compounds that are hydrocarbons are made of hydrogen and carbon. That's that simple. Anything that's made of carbon is organic. So anything that has carbon atoms are organic compounds. So these are actually organic compounds, but also contain hydrogen, therefore they're hydrocarbons. The word organic in chemistry means that it contains carbon. It means nothing else besides that. If something is organic, it contains carbon atoms. That's it, period. So, but then if it's a hydrocarbon, not only does it contain carbon atoms, it also contains hydrogen. So you can follow along on this. And the answers for some of the things are actually included, which is okay. But I have that on a separate thing so I can annotate some stuff. And then I have some other examples besides what's in the slide. But you need to be able to write formulas for and name hydrocarbons. Let me switch to a different screen here. See, that looks okay. All right, so the first slide on that, there are rules for naming all kinds of different things in chemistry. And, over time you get used to how the names and formulas work. But it turns out that you're actually pretty familiar with a bunch of these hydrocarbons. You've heard the names of these chemicals before, but now you're going to get to find out what the formulas are and how they go together. But hydrocarbons are covalent compounds, so they're covalently bonded where electrons are shared between atoms. They're compounds that contain only carbon and hydrogen. Uh, the names of the compound is determined based upon how many carbon atoms there are and what types of bonds exist between the carbon atoms. And I'll show you how those bonds are related to Lewis structures and related to valence electrons. But for now, you can identify the compound based upon whether the bonds are single bonds, double bonds, or triple bonds. And I'll show you how that works briefly too. So there are a couple rules for naming hydrocarbons. And one of them is you got to look to see how many carbons are present in the compound. And the number of carbons that are present in the compound tells you about the part of the name with a number prefix. And there are a couple different sets of number prefix rules we use in chemistry. And there's a specific set of rules that are used with organic compounds for those prefixes. So we had number prefixes like mono, di, tri, tetra, stuff like that. But for hydrocarbons, the number prefixes work in a different scheme. The prefix for 1 is meth, 2 is eth, 3 is prop, 4 is bute, 5 is pent, 6 is hex, 7 is hept, 8 is oct, 9 is non, and 10 is like dis or des, depending upon what compound it is. Some of these number prefixes you're familiar with for other things, like a 5-sided shape is called a pentagon, 6-sided shape is a hexagon, 7-sided shapes, heptagon, octagon, nonagon, decagon. We have months of the year, October, November, December, but that's funny because October is the 10th month, November is the 11th month, and December is the 12th month. But they're October, November, December because June and July were shoved into the summer and it pushed all the months ahead. So like September, 7 is also sept instead of hept, but here we always use hept. The months October, September, October, November, December literally means 7th, 8th, 9th, 10th month. But when June and July were inserted in the calendar, September, October, November, December got pushed ahead by 2 months. So the only months in our calendar that are named for numbers aren't even the correct numbers, which is kind of silly. Some of these prefixes, other prefixes you heard for other uses. So in shapes, pent and hex are used, but not for hept necessarily. We usually use like sept. But meth, eth, prop, and bute are common for the beginning of hydrocarbons. So you'll see what I mean by you've seen these names before. That's one part of the rule. The other part of the rule is, oh, and there's a mnemonic for the first 4 prefixes. Monkeys eat peeled bananas. People use that as a mnemonic. You'll also find other mnemonics online for knowing all 10 of the hydrocarbon prefixes. Some people remember monkeys eat peeled bananas for meth, eth, prop, bute. But the second rule has to do with the end of the name. And the end of the name for hydrocarbons always ends with ane, een, or ein. It's pronounced ein, even though it's Y-N-E. It looks unusual, but you'll see how it works out. The name ane, een, and ein refer to whether the compound has single bonds, double bonds, or triple bonds. And one way to remember this is those letters A, E, and Y, they're in alphabetical order. So A is at the beginning of the alphabet, E is further, and then Y is toward the end. If a compound only has single bonds, its name will end with ane. If the compound has a double bond, it'll end with een, and if it has a triple bond, it'll end with ein. And there are different applications for ane, een, and ein. The number of hydrogens doesn't really make any difference, and we're not going to name compounds with more than one multiple bond. These names for hydrocarbons will be common as we study different types of reactions, especially combustion reactions, because most of these alkanes or most of these hydrocarbons are fuels. We use them as fuels. All right. So here's how it all kind of goes down. There's a class of compounds that are called alkanes. And alkanes are hydrocarbons that have only single bonds. And what it has to do with is how many carbons there are in a chain. So for instance, there's a compound whose formula is CH4. It's a carbon with 4 hydrogens. Now let me show you how this goes together. When we did stuff with uh, uh, valence electrons, I showed you about drawing the Lewis dot structure. Carbon has 4 valence electrons, so you can make its Lewis structure like this. So there's carbon, and I've shown 4 dots around it. Those 4 dots indicate 4 valence electrons that carbon has. Carbon's in group 15 of the periodic table. But you know that carbon wants to have 8 valence electrons. And then hydrogen, its Lewis dot structure, has only 1 dot, because hydrogen only has 1 electron, and that 1 electron is a valence electron. And hydrogen wants to have 2 valence electrons. In covalent bonding, atoms will share electrons to end up with a situation where they've got a full valence structure. So this example down here, where it says CH4, which is the formula for a chemical compound of methane, how you could draw its Lewis dot structure. Oh, excuse me, I had to sneeze. Is if you've got this carbon atom and you got some hydrogens that are going to come in near it, you can almost look at it as hydrogens are going to like plug into the carbon. I'll color code it so that hydrogen's 1 valence electron goes here, hydrogen's like this, another hydrogen here, and another hydrogen here. And these color-coded dots indicate which atoms each of the electrons belonged to. Whenever 4 hydrogens bond with a carbon, this carbon atom now has 8 valence electrons around it, and each hydrogen has 2 beside it. So it turns out that these pairs of shared electrons get to count for both of the atoms. What I mean by that is each of these hydrogens gets to count both its own hydrogen, its own electron, as well as 1 from each of the carbons. At the same time, this carbon gets to count all 8 of these electrons as its own. So in covalent bonding, when you're sharing these electrons, those electrons that are shared count for both of the atoms. We know that to be true. So instead of having it color-coded, I could draw it like this, showing all of the electrons present with carbon and hydrogen. But it takes a long time to draw that. So instead of drawing it with individual dots, we replace a pair of bonded electrons with just a single line. So this notation with a single line indicates a single bond. What I mean by a single bond is that it's a single pair of electrons that are shared between the pairs of atoms. So that's why for CH4, this formula can be shown as a carbon with 4 hydrogens coming off of it. These individual single bonds are a single pair of electrons that are shared. If you have, let's see, if you have 2 carbons, let me show you like this. So if I take and put 1 carbon here and put another carbon beside it, I'll put this carbon in green. Oops. There we go. I can put 2 carbons side by side. When you put 2 carbons side by side, these individual pairs of electrons end up to be like a shared pair between the 2 carbons, but then I still got these lone electrons around the outside. So there could be another hydrogen here, another hydrogen here, one up here. So I've got all these other hydrogens that have to go around it. And again, that's kind of complicated to draw, so it's a whole lot easier to just draw it like this. So that's an example of a compound that has 2 carbons in a chain with hydrogens all coming off of it. And based upon the naming scheme, this one was called methane. It has the meth at the beginning, and 2 is eth. So that one's ethane. Eth is the prefix for 2. You can keep on going. You can have 3 carbons in a row, and I'll show you some examples of that. So, for example, if a compound ends with ane, it is a singly bonded chain of chain of carbons. Let me get somebody else coming in. Here we go. If it has an ine, it's double bonded. Or I'm sorry, it's triple bonded. And if it ends with ene, it's double bonded. So, for example, if you have 7 carbons and it's an alkane, it's called heptane because 7 is a prefix, or hept is a prefix for 7. If you have 9 carbons and you're an alkane, you're called nonane. If you have 2 carbons and you're an alkyne, you're called ethyne. If you have 2 carbons and you're alkene, you're called ethene. So these prefixes, hept, eth, non, bute, and prot, they refer to the numbers of carbons. And then the ends always tell you about whether they're single, double, or triple bonded. So if it ends with ane, they're all single bonds. If it ends with ine, those are actually the triple bonds. And if it ends with ene, those are the double bonds. I'll show you with practical examples to make it a little bit simpler. So for instance, this one that says propene, prop is for 3. So there's 3 carbons, 1, 2, 3. And ene means there's a double bond. So let me show you how a double bond works. A double bond is when 2 pairs of electrons are shared between atoms. So you see in this structure here, there's a carbon and another carbon, and there's 2 lines that exist between them. That means that 2 pair of electrons are shared. I can draw this carbon, put 2 of its electrons on one side, and then have 1 electron here and 1 electron here. So those are the 4 electrons for carbon. These 2 hydrogens are like a hydrogen here and a hydrogen here. But that carbon's bonded to another carbon. Let me put that one in green. And it has 4 electrons. 1, 2, 3, 4. And then there's another carbon on the right. And it has 4, 1, 2, 3, 4. So the idea is that you've got these dots. Here I've color-coded them, referring to the numbers of electrons that each individual atom has. And then the hydrogens are going to fill all those in to fill all those blank spaces around the compound where there are unpaired electrons. And in this case, the hydrogen can only make a single bond. So there's a single bonded hydrogen here, single bonded hydrogen here, single bonded hydrogen, another single, single, and single. The bond between these 2 carbon atoms has only 1 pair of shared electrons, but the bond between these 2 carbons has 2 pairs of shared electrons. And that's why in that structure for propene, these 2 pair of electrons are replaced with 2 lines. So the idea is that instead of drawing all those dots, you can draw a line to represent a pair of shared electrons. So if 2 electron pairs are shared, it's a double bond, and we draw 2 lines. If 3 pairs of electrons are shared, that's a triple bond, and there are 3 lines. There's no such thing as a quadruple bond. That just doesn't exist. So there are these single, double, or single or double or triple. All right, we're going to go through some specific examples. So here's some examples of compounds that you know of. Natural gas, which is kind of become famous here in Pennsylvania. We used to never really get much natural gas out of the ground, but once fracking started, about a decade and a half ago or so, we have natural gas wells all over the place in Pennsylvania. And natural gas is the kind of nickname for methane. So if you have a gas range in your home, especially live in the city, or you have gas heat in your house, you have a gas line that comes to your house, that gas or natural gas is in the gas phase. It's not gasoline, but it is methane. And methane is just CH4, a single carbon. The next gas is ethane. It doesn't have any practical common uses. But then propane, this prop is for 3. Propane is, you'll see how the naming scheme uh, goes, but it's C3H8. There are 3 carbons in a row. So propane has 3 carbons, all single bonded with hydrogens. Sorry, my pen is like a little slow. So propane is another fuel. Propane, you can buy it in bottled gas form. Sometimes, especially live in a rural area, you might have a propane tank outside your house, and a propane truck comes and refills it. You can exchange these at like hardware stores and stuff, or get them refilled sometimes in person at uh, feed supply places. They're commonly used with gas grills, or if you go camping. Most RVs run off of propane because it's relatively inexpensive for a transportable gas. 4 is butane. The BUT, it's not pronounced but, it's pronounced bute. We don't say butane, we say butane. Like nobody says butane. I mean, it might seem cool to say that, but it doesn't make any sense. We say butane. Butane is 4 carbons in a row. So butane is what's used in lighters, uh, all kinds of lighters. So it turns out that butane uh, is easily stored at not as high of pressure as propane. So propane tanks have to be in steel cylinders, and the pressures are fairly high. Butane doesn't have as high of a vapor pressure, so it turns out it's a liquid, but it's easily vaporized. So you might know that if you push down on the valve on a butane lighter, liquid doesn't come out, gas comes out, but the pressure inside here is very low, so it can be as a liquid. And then it turns out whenever you buy fuel, these fuel ratings, like 87, 89, 93, you might know that that's called the octane rating. And octane means 8. So it's an 8-member chain of carbon atoms. And the octane rating is actually the ratio of heptane to octane in the fuel. But it's not always that fuel is always heptane and octane. So what that means is if you buy 87 octane, that's 13% heptane, 87% octane. Except the fuel isn't always heptane and octane, but that's the effective uh, ratio if it were to be a straight ratio of those. 93 is 7% heptane and 93% octane. So the octane rating, or the different grades of fuel, like whenever you refuel a car, you buy different grades of gasoline, and that's really the ratio of heptane to octane. So those are common places you see those kinds of compounds. Okay, so here's some strategies, and we'll do some examples. Naming a compound with its structure, you count the number of carbons and look to see if it's single, double, or triple bonds. Then you pick the right prefix and the right ending. So the number of carbons tells you about the prefix, whether it's double or triple bond tells you about the ending. If you're writing a compound name from a formula, uh, you look to see what the ratio of carbons to hydrogens is in the compound. And I'll show you how this works, but there's a generic formula to determine whether something is alkene, alkane, or alkyne, and it has to do with the numbers of carbons and hydrogens relative to each other. So, for instance, um, ethane, because it ends with ane, means they're all single bonds, and the eth is referring to 2. This is the number of carbons. And then the number of hydrogens is determined based upon whether they're single, double, or triple bonds. This little formula here, where it says CXH2X plus 2, if it's an alkane and if it's ethane, it's C2 and then it's H, and the number of hydrogens is 2 times the number of carbons plus 2. Or it's like C 2 times 2 plus 2. But we don't write it like that. It's C2H6. In other words, 2 times 2 is 4. 4 plus 2 is 6. So ethane is C2H6. On the other hand, if it's ethene, the little formula says CxH2x. Ethene still has 2 carbons, but the number of hydrogens is just 2 times, in this case, 2 or 4, C2H4. If you have ethine, the formula generically is Cx times H2x minus 2. So it's like C2H2 times 2 minus 2. Well, 2 times 2 is 4. 4 minus 2 is just 2. C2H2. So in every case, alkanes, the number of hydrogens is always double the number of carbons plus 2. For alkanes, or for alkenes, the number of hydrogens is always double the number of carbons. And for alkynes, the number of hydrogens is always double the number of carbons minus 2. I'll show you how that works with practical examples in just a second, but these little formulas are important to have handy too. Okay, so for example, here are some structural formulas, and you can just count numbers of carbons and hydrogens in the formula to help you figure out how many carbons and hydrogens you've got. In this case, each of these cases, you can see whether they're single, double, or triple bonds. So here, you can count the number of carbons. You got 1, 2, 3, 4, 5, 6. Let's see. So 1, 2, 3, there's 6 carbons. So that's like C6. And then the number of hydrogens, well, I'll start up here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So C6, H14. Because there are 6 carbons, 6 is hex. And because all of the bonds in here are single bonds, there's no double or triple lines, it's an alkane. This is hexane. Another reason you know that it's hexane is if you look at the relationship between these two different numbers, 14 is 6 times 2. That wrote real bad. 6 times 2, well, I'll do it 2 times 6. So it's in the same form, plus 2. 2 times 6 is 12, plus 2 is 14. And the rule for naming alkanes or writing formulas for alkanes is that the number of hydrogens is always double the number of carbons plus 2. So that one turns out to just be hexane. In this case, you got 4 carbons. 4 is bute. And you can see in this compound, there are 3 bonds between these 2 carbons. That means that it's an alkyne. It ends with "-ine". It's butine. Also, if you count the number of hydrogens, so here this was C4 and then H6. Alkynes, they have that formula CX. That didn't write well at all. CXH2X minus 2. You see, like 2 times 4 is 8, and 8 minus 2 is 6. So based upon the generic formula for the relationship between numbers of carbons and hydrogens, that formula checks out, and all alkynes have that generic formula. So this one's hexane, ane because they're all single bonds, butine, bute because there are 4 carbons, and ine refers to the fact that there's a triple bond. All right, so here's some examples. In the example problems, we'll just do a couple of these real quick. There are examples of formulas and names. And, oh yeah, no, this is more examples. Okay, so C5H10, I only have like 2 minutes left. So C5 is pent, so I know that that's got to be pent. And then here, the number of hydrogens is exactly double the number of carbons. And if the number of hydrogens is double the number of carbons, it has to be an alkene. That's pentene. C2H6, 2 is eth. And then the number of hydrogens is 2 more than double the number of carbons. It follows this rule for alkanes. See, if there are 2 carbons, if you put 2 times 2, you get 4, and 4 plus 2 gives you 6. So that's ethane. For C2H2, there's 2 carbons, so that's eth again. But the number of hydrogens is double the number of carbons minus 2. It follows this formula, ethyne. All right, and then these 2 examples real quick. Propene, prop is 3, so it's C3. And the rule for the number of hydrogens is if it ends with "-ine", you take the number of carbons, double it, and subtract 2. So if it's C3, this is H, 2 times 3, which is 6. 6 minus 2 is 4. Let me think. 1, 2, 3. Yep, that's good. And then hexane, hex is 6, so it's C6. And then it ends with ane. It's got to be, if there's 6 carbons, 2 times 6 is 12, plus 2 is 14. C6H14. All right, so there's an example problem set in the, I have like 1 minute left. There's an example problem set in the folder. Let me go back and share this real quick. It says Naming Hydrocarbons Practice, and it has examples of names and formulas for compounds, and you need to try that. So this Naming Hydrocarbons Practice in the folder, when you click on that, there are structural formulas at the top that show numbers of carbons and hydrogens. And then on the next page, there are written examples of alkanes, alkenes, and alkynes with numbers of carbons, and then also some formulas to write names. So either write the name or write the formula for the compound based upon the clues that are given. So do those as practice, and we're going to go over those tomorrow. All right, I guess you got to get to your next class. If you have questions, you can turn on your mic, ask, or put it in the chat, like whatever. But otherwise, I'll see you tomorrow.